Now.
Okay. Good morning. I am Rajesh Kumar, done MTech from IIT Kharagpur. I am going to discuss the thermodynamics. And these are the contents of presentation. First of all, I will discuss about the introduction of thermodynamics. Then I will go in terminology, types of systems, temperature, and then I will discuss about the ideal and perfect gases. Then I will tell about the concept of the heat, work, internal energy, and entropy. Then I'm going to just give the idea of reversible process, a state and path functions in thermodynamics, a spontaneous and driven process. Then I will tell about the concept of the heat capacity. And finally, I'm going to discuss about the thermodynamic processes, law of thermodynamics. And last but not least, I will discuss about some questions which are already come in some competitive exams. So coming to the next slides. So first of all, thermodynamics. Thermodynamics is the branch of science in which we deal with the system levels. Here we are not dealing with the interaction of the individual particles. Instead of this, we are dealing with the complete systems like temperature and pressure. Here some terminology which we are going to use in the thermodynamics. First of all, are the systems. Systems are nothing but it is a region where we focus our attention for the study. In this example, you can see this is the block of AU. This is the systems where we will focus our study, but in the surrounding of this block of AU, this is the water. So this is water is considered as the surrounding, and this AU block is considered as the systems. So when we are combining this complete two systems, means block of AU and the surrounding, it will becomes the complete universe. So from this discussion, we can say that universe is the combination of the systems and surroundings. Coming to the next slide. Coming to the next slides, the systems are mainly three systems: open systems, closed system, and isolated system. In open system, there is transfer of matter as well as the heat. So as an example, we can take a beaker in which we have, if we are adding the water. So here, when we are adding the waters, that means we are transferring the mass. And same times when we add the water in the beaker, so heat contents in the waters can also be transferred. So here, when we are adding water in the beaker, we can see here it is the transfer of the mass as well as the heat. So this is the good example of the open types of systems. Coming to the next systems, closed systems. In these systems, matter cannot be added or transferred, only heat can be added or removed. So if you want to take the example, you can see when we are going to cool a closest water bottle in the fridge. So in this case, we are not going to transfer of the matter. Means we are not transferring the mass, only we are transferring the heat. Because initially when we are put the water bottle in the fridge, so water temperature is little bit high, but after some times water temperature is low because only transfer of the heat, but amount of water contents remains same. So this is the example of the closed system. Coming to the next isolated types of system. In these systems, there is no transfer of the matter and no transfer of the heat. So in the example, you can take the thermos flask. In thermos flask, the amount of matter also not transfer. At the same time, heat also we cannot transfer. So this is the isolated systems. So in the next slide, I just make a summary of the types of systems. So this is in open systems, all interactions possible. That means we can transfer mass, work as well as heat. In the closed systems, only matter cannot enter or leave, but only heat can be transferred. In isolated systems, no interaction are possible. Means no mass as well as no heat can be transferred. There is some other kind of system also, insulated system. In heat cannot be leave or enter the systems. In rigid systems, no mechanical work is allowed to do. In semi-permeable type of systems, only certain species can enter or leave. But in these open systems, complete mass can enter or leave. But in case of semi-permeable, only certain species can enter or leave. So there are some small difference between open and semi-permeable types of system. Now coming to the next slides, I will discuss about the temperature, because we are going to study the thermodynamics. So in thermodynamics, everywhere we are discussing with the temperature or transfer of heat. So temperature is the measurement of intensity of heat, or we can say heat flow from body of higher temperature to one body at lower temperature. So we can take an example here. There are two blocks, blocks A and B. So blocks A having the higher mass, it is about 100 kg, and block B is the only 1 kg. But temperature of block A, that means higher mass, is 10 degrees centigrade, but the temperature of a small block is 500 degrees centigrade. Due to the higher temperature of the block B, that means a smaller block, the direction of the heat flow is from a smaller block to the bigger block. So that means we can say that heat transfer cannot depend on the matter. It is depend upon the amount of heat contents. That's why in this case, transfer of heat, it passes from the a smaller block, that means 500 degrees centigrade, to the bigger block, that is the 10 degrees centigrade. So this is the concept of the temperature. So these are the some scales we are using for the temperature measurement. So Kelvin is the scale we are using for the absolute scales. So 0 Kelvin and temperature below that, in actual practice, it is not possible. And Celsius, Fahrenheit, etc. at the relative scales. These are scale we are using just for the study purpose. And in classical manner, if we say 0 Kelvin, at 0 Kelvin temperature, perfect crystal system has 0 entropy. That means randomness of the system is 0. So here are the some conversions formula. By that we can transfer one scale to another scale. Suppose we have the temperature in the Fahrenheit and we want to transfer in the Celsius. So Fahrenheit value we will put in this formula, we will get in Celsius. In same manner, if we transfer the scale temperature in the Kelvin, so this Fahrenheit value we will put in this formula, we will get in the Kelvin. In similar manner, we can convert Celsius to Fahrenheit, Kelvin, and Kelvin to Fahrenheit, Celsius, etc. So here we can understood, if we having the temperature in any particular scale, we can get in the other scale also by utilizing this formula. So these are the concept of conversion of the scale to the temperature measurement. So just before going in the details, I am giving the some idea about the ideal and perfect gases. What is ideal and what is perfect gases? In ideal gas, molecules do not interact with each other. So this is possible only in noble gases. An ideal gas also obey the equation PV is equal to nRT. And apart from this, as molecules of ideal gas do not interact with each other, that means internal energy of the system is expected to not depend on the volume of the systems. So that's why we can write like this: del U upon del V equal to 0. So this is the example of the ideal systems. So if we consider the perfect gases, so perfect gases are those which flow above these two conditions. Means any gas, if this follow PV is equal to nRT equations, and apart from this, it will also obey del U upon del V equal to 0, then that gas we can say it is the perfect gas. So if we consider the internal energy, it is the function of temperature and volume. So here we see in these points that the internal energy is not dependent upon the volume. So this is the case of the perfect gases. So we can say that for perfect gas, internal energy depends only on the temperature, that you can see here. It is not depends upon the volume. But apart from the perfect gases, other gas internal energy will depend upon the temperature as well as the volume. But same formula, when we are dealing with perfect gases, internal energy only function of the temperature. In the next slides, we are giving the concepts of the heat and work. Heat is the transfer of energy as the result of temperature difference. And heat is also not an entity, it is even a form of energy. It is a mode of transfer of energy. Any body did not contain the heat, it contains the internal energy. So heat involves random motion of the matter or constituent entity of the matter, like gas molecules in the gas cylinder, water molecules in the cup of water, atom vibrating in the block of copper. These all are the example of the heat contents. Now we are coming to the work. what is work? Work is nothing but it is the displacements against some resisting force. So in mathematical form, we can write work equal to F into D. So when we have to calculate the work, we require the force, and the same time we require the displacements. When we give these two data, we can calculate the work, and the unit of work is the joule. So in other form, work is defined as when we are lowering the weight, it can do the work, or you can also say when motion of the piston can do the work, flow of electron in the conductor, it can also do the work. So these are the some examples that by which we can see how work can be considered. Now internal energy, because in the thermodynamics everywhere we are dealing with the internal energy, we are not dealing with the temperature. So internal energy is defined as the energy associated with the random disorder motion of the particle. Random disorder motion consider translational motion, rotational motion, and vibrational kinetic energy. That you can see here. This is the translational motion, this is the rotational motion, and this is the vibrational motion. All these motions combined together become the it will contribute to the internal energy. The unit of internal energy is joule, or we can also write in the kilojoule. So when change of internal energy is greater than 0, we can say that it is the gain of internal energy. On the other hand, when change of internal energy is less than 0, we can say that loss of internal energy. These are the some mathematical concepts that we will discuss in the coming slides. Coming to the entropy. Entropy is the nothing but it is the degree of randomness. In short form, we can say like this. But entropy is the measure of the system's thermal energy per unit temperature. That I also written in the mathematical equation form. This is the change of entropy. It is equal to the thermal energy per unit temperature. That is unavailable for doing the useful work, because useful work is obtained by the order molecule, but entropy is the not an order molecule. That's why I written here per unit temperature, that is unavailable for doing the useful work. That much energy is not available for doing the some important kinds of work. So that is the entropy. Entropy is written by alphabet letter S, and change of entropy we can represented by del S. So here del S is equal to del Q by T is the expression for calculating the entropy, where del Q is the change of heat energy and T is the temperature. Now coming to the reversible process. Reversible process is one where infinitesimal changes in the condition of the surrounding lead to the reversal of the process. That you can understood by these diagrams. Here you can see this is the block with temperature T, and these are the surroundings with temperature T minus del T. So here block having temperature T and surrounding having temperature T minus del T. So it is little bit lesser than the block. So obviously heat will be transferred from block to surrounding. But on the other hand, when we increase the temperature of the surrounding from T to delta T, so in this case, temperature of the surroundings becomes higher than the block. So in this case, temperature will be transferred from surrounding to the block. So you can say here, that's the reversal of the process. So this is the example of the reversible process. You can also see here how work done is calculated in the reversible process. It is a closed pistons and cylinders. Example, when we are applying the force P in this direction, piston be moved in inward direction. So here we can say that this is the example of work done on the systems, because we are moving the piston in the inward direction. So this is the example of work done on the systems. But when applying the force in the opposite direction, means from this way. So in this case, piston is moving in the outward direction. So this will be the example of work done by the system. So when we are dealing with the work done on the system, so delta W work done can be calculated like this, minus P into delta V. So the system is the closed equilibrium during the whole process, thus making the process reversible. So in reversible process, we can get the maximum work done. So in same equations, if we will dealing with the work done by the system, this will come the plus sign. So this is the concept how we will calculate the work done in the reversible process. Now coming to the state function and in the thermodynamics. In thermodynamics, mainly we are dealing the two types of system, a state function and the path functions. In a state function, a property which depends only on the current state of the systems as defined by temperature, pressure and volume. It is called the state function. You can see here in this example, here some points is P. So from at the point P, something is coming like this. At the same point, some other particle is coming like this. But final position is the same. Either it is coming via path C1 or either it is coming via path C2. But final position is the same. But when we are going to calculate the potential energy, so it will calculate the height from the ground to the center of gravity of this point P. So this is the formula mgh. So we required only final height. So potential energy not depend on the path. So either it is coming through C1 path or either it is coming through C2 path. But final position is the same. So this is the example of the state function. That means the function which does not depends on the path. In thermodynamics, internal energy also example of the state function. Now coming to the next slides, when we are going to calculate the internal energy, we can calculate EH means at the energy at the higher level, UL energy at the lower level. When we are making the difference between the energy at higher level, energy at lower level, we will get the work done. And the internal energy of the isolated system with neither heat nor mass that we already discussed in the previous slide is the constant in this case. And this is also formula of the first law of thermodynamics that we'll discuss in the upcoming slides. And for cyclic process, this change in internal energy is 0. For the any cyclic process, when we are going to calculate the change of internal energy, it should be 0. Now coming to the path function. It is the property of the system that depends on the path by which a system achieves a particular states. That we can see here, work and heat transfer both are the example of the path function. This is the PV diagram. In PV diagram, these are the two positions, position 1 and position 2. So from position 1 to position 2, we can follow the three paths, path A, path B, path C. So if we are consider path A, this is the case of the PV diagram. So in this case, work done, we cannot write W2 minus W1. That means work done at the final position and initial position, it is not written like this because it depends upon the path. When we are going to calculate the work done, we have to calculate the area enclosed by this curve A. So when we are going to calculate the area by curve A, we are getting this much area. In similar manner, when we are going to calculate the area by curve B, this straight curve, we are getting little bit lesser amount of area compared to previous case. And again, when we are going to calculate the area enclosed by C curve, again it will little bit lesser compared to B curve. So what we are observing, work done depends upon the area enclosed by curve. It is not depends upon the initial and final position like previous case. In the internal energy or potential energy, that is depend only on the initial or final position. It not depends upon the path, how it's covered. But in this case, it is not true. It depends upon the paths. And for heat also it is not true. We cannot write Q2 means heat at second point and minus Q heat at first point, it will give the change of heat. This is not true because this is also depends upon the path. So we can say that work and heat transfer both are the path function and internal energy and potential energy are the point function. So in this manner we can separate any parameter, either it is the path function or the point function. Now we are going to just give some concept of a spontaneous on the driven process. In a spontaneous process is one which occur naturally. Means in this case we are not going to give any extra force. That you can see here. This is the ball resting on the uphill. So when we are giving even a small disturbance, this ball will come and fall down automatically to the ground. because of the gravity force. So in this case, we are not providing any external force. It will come automatically by the force of gravity. So this is the example of a spontaneous process. But same thing, if we have to climb a hill, suppose ball is resting on the ground and I have to make climb on the up position. So that will not go spontaneous. In that case, we have to apply the force. Then only this ball will able to go from this ground level to this top level. So this is the example of the driven process. So this is the difference between a spontaneous and driven process. We can also take example. When we are freezing a water at minus 15 degrees centigrade, suppose any water having current temperature is 50 degrees centigrade, when we want to freeze it, so it will not automatically freeze. We need a refrigerator. In refrigerator, we are providing the external force. So this is the force of, this is the example of the driven process. Now coming to the heat capacity. Heat capacity is the amount of heat required to raise a unit mass of the substance through 1 degree centigrade temperature. That means for any substance of mass 1 degree centigrade, how much heat is required to raise its temperature to the 1 degree centigrade? That is the heat capacity. Heat capacity can be defined in two ways: heat capacity at constant volume and heat capacity at the constant pressure. At constant pressure, some heat supplied goes into doing some external work also. But when we are dealing at constant volume, it is not doing the external work because volume is constant. When volume is constant, piston will not able to move. So in that case, it will not able to do some work. So in mathematical form, heat capacity at constant volume, it is represented by CV, is written at delta E upon delta T at constant volume. So we can also say that it is the slope of the potential internal energy, because E is the internal energy. So it is the slope of internal energy with respect to temperature. So this is the mathematical form of heat capacity at the constant volume. In similar manner, we can write heat capacity at the constant pressure, and it is represented by Cp. So here, heat capacity at constant pressure is the slope of enthalpy with temperature. Heat capacity is constant volume by the slope of internal energy with temperature. And this is the slope of enthalpy with temperature. So this is the difference between heat capacity at constant volume and heat capacity at constant pressure. And we can also calculate by this mathematical form. Now, unit of the heat capacity is joule per Kelvin per mole. We can also write in the kilojoule. Heat capacity is the extensive property. Extensive property is one which depends upon the amount of matter. We take an example. Through this example, you can get a clear idea about the heat capacity. If a substance has the higher heat capacity, then more heat has to be added to resist temperature. That means higher heat capacity need higher heat to raise unit degree temperature of unit mass. That I already told. So here I am taking the two things. First thing is the water. Second thing is air. The heat capacity of the water is 4186 joule per Kelvin per mole. But the heat capacity of the air is only 29.07 joule per Kelvin per mole. So here we can see that heat capacity in water is higher than heat capacity of the air. That means for heating the water, we need high heat compared to air. So this is the concept of heat capacity. You can understand easily. At 0 degree Kelvin, the heat capacity value is 0. That means near 0 Kelvin, very little heat is required to raise the temperature. That much amount of heat we have to give. So because here heat capacity is the 0, that means we need very little amount of energy to raise the temperature of that sample. So that is the concept of the heat capacity. Coming to the thermodynamics process. So thermodynamic process, mainly we have the isothermal process. In this process takes place at the constant temperature. Isothermal means temperature will be constant. So through this curve, you can see that this is the curve of the constant temperature and this is the pressure versus volume plot. in pressures versus volume plot, this is the curve of isothermal process. And when we are going to calculate the work done, we have to calculate this area enclosed by curve. This will give the work done. So in example, you can take when we are going to freeze a water to ice at minus 10 degrees centigrade. That means water is already having a temperature minus 10 degrees centigrade. So converting it into ice, we not need any heat transfer. So temperature difference. So in this case, we can say that the freezing of water to ice at minus 10 degrees centigrade will occur at constant temperature. So this is a good example of isothermal. Coming to the isobaric process. So isobaric process is the process that will take place at the constant pressure. So you can see here in PV diagram, this is the curve that is pressure is constant. Again, in same curve, if you want to calculate the work done, we have to calculate the area enclosed by curve. So this will give the value of work done. So if you want to take an example, in this case, you can consider heating of water in the open air. Because in open air, pressure is constant, that is the atmospheric pressure. So that means we are dealing with the constant pressure. So this is the example of the isobaric. Now, isocuric process. In this process, volume is constant. So in PV diagram, you can see here, this is the curve. Here, volume is constant. Means volume is not increasing. It throughout from a starting to final, volume is constant. So if you take the example, you can see here, heating of gas in the sealed metal container is a good example of the isocuric process, because container is the seal. That means we are not going to change its volume because the container is sealed. So this is the example of the isocuric process. Now coming to the adiabatic process. In adiabatic process, we have the del Q is 0. That means change of heat is 0 throughout the process. That means no heat is added or removed from the systems. So this is the curve, green curve. You can see that this is the process of adiabatic in the PV diagram. So in adiabatic process, delta T not equal to 0, but Q is 0. So this is the adiabatic process. Now coming to the next slide, we are giving these two examples of the cyclic process and reversible process. Cyclic process is that in which initial position and final position is the same. You can see here in this. Suppose we are starting from point 1, it will go 1 to 2, 2 to 3, 3 to 4, 4 to 1 by various process. 1 to 3, that is the isentropic process. 2 to 3, constant volume process. Again 3 to 4, isentropic process. 4 to 1, constant volume process. So finally, we are starting from 1, and again it comes from point 1. That means initial and final states are same. So this is the example of the cyclic process. In reversible process, the system is close to equilibrium at all the times. That means suppose when we are giving a small disturbance in any position, the system can restore its universe. So reversible process can be represented in PV diagram by continuous curve. So here green curve you can see here. This is the reversible process. And irreversible process can be represented by dotted curve. Here you can see from point 1 to point 2. This is the dotted curve. This is the reversible process. So in irreversible process, suppose I given any disturbance and any instance, the system will not able to restore its universe. But in reversible process, if we are giving any disturbance and any instance, the system can restore its original position at any time. So this is the reversible and irreversible process. Now coming to the next slides, we are coming to the laws of thermodynamics. In thermodynamics, we are dealing with zero law, first law, second law, third law of thermodynamics. According to zero law of thermodynamics, suppose A and B are the two systems, and these two systems are in thermal equilibrium with each other. And we are consider B and C are other systems which are also thermal equilibrium in each other. So if A and B are thermal equilibrium and B and C are thermal equilibrium, then these two systems we are already in the thermal equilibrium. This is the zero law of the thermodynamics. Now coming to the next slides, that is the first law of the thermodynamics. In the first law of thermodynamics, internal energy of isolated system is the constants. if in the first law of thermodynamics, if closed system may exchange energy as a heat of burst, let us consider the closed system at rest without the external field. So in mathematical form, the first law of thermodynamics can be written as delta U is equal to Q plus W. Here Q is the heat flow in the system, W is the work flow. So U is the internal energy and delta U is the change in internal energy. So as I already discussed in the earlier slide, the change in internal energy is the state function. That means it depends upon only initial and final position. But Q and W here not are the state function. This is the path function. Because this work done will depend upon the path. So here Q and W are the path function and this is the point function. And for the infinitesimal process, equation 1, same equation can be written as du is equal to dq plus dw. And when we are dealing with the system and surroundings, so change in internal energy for the system plus change in internal energy in the surroundings equal to 0. That means for any system and surroundings, change in internal energy, if we are adding for systems and surrounding, it will become 0. Now coming to the second law of thermodynamics. In the second law of thermodynamics, two statements are given. First is the Kelvin statements. According to Kelvin statements, it is impossible to build a cyclic machine that will convert all of its heat into the work. In another way, we can say that it is impossible to construct a cyclic machine that will be completely convert its heat into the mechanical work. That you can see here. This is the heat reservoir. This is the heat engine. Heat is coming from the heat reservoir. All heat is converted into work. That is not possible in the actual practice. That is only hypothetical, because so many types of losses are also there. So complete heat, how much amount of heat we are taking from the system, same amount heat will not converted into 100% of work. This is not possible in the actual practice. This is the Kelvin statement given for the second law of thermodynamics. But in actual, when we are taking the heat from the heat reservoir, some amount of heat can be used for doing some useful work, and some amount of heat can be wasted on stored in the reservoir. This is possible in the actual practice, but this condition is not possible. This is the Kelvin statement given for the second law of thermodynamics. Same coming to the Clausius statement. For the second law of thermodynamics, for the same second law of thermodynamics, Clausius told that heat can flow from the cold body to hot body by doing the external work. Means heat will always from hot body to cold body. But when we are trying to flow the heat from cold body to hot body, it will flow only by doing some external work. This is the Clausius statement for the second law of the thermodynamics. The Kelvin and Clausius statement for the second law are equivalents. That is, if we are violate the Kelvin statements, then we will automatically violate the Clausius statement also, and vice versa. When we are combined Kelvin and Clausius statement of second law of thermodynamics, we can say that entropy of the closed system will increase during any spontaneous changes. And if we are considering the universe to be a closed system, means that when we are considering complete universe as a closed system, then entropy of the universe will be increased during any spontaneous changes process. These are the two statements when we are combined Kelvin and Clausius statement. Now this is the heat engine and the work engine. In the heat engine, our main objective is to produce the work. That means we can see here, this is the heat reservoir. So heat reservoir will give the heat to the heat engine. So heat engine will do some work. Here some work done will get. And apart from this, also reject some heat that will go store in the cold reservoir. So this is the work engine. So here we can see that work engine is mainly using for producing some work. This is some useful work. Coming to the other hand, that is the heat engine. In heat engine, our objective is to transfer heat from cold body to the hot body. That means for transferring heat to the cold body, from cold body to the hot body, we need some external work according to the Clausius statements. So that means from heat is transformed from, this is the cold body, and heat will flow from cold body to the hot body. Natural way it is not possible. It will not go from cold body to hot body. But same thing we are achieving by doing some external work. Here we are giving some external work to the cycle engine. That external work help to flow heat from this cold body to the hot body. Same thing we are doing in the refrigeration. In refrigeration, we are extracting the heat from the cold reservoir. Refrigerator is the cold reservoir. So by doing the external work by the compressor and all these instruments, so it continuously reject heat from the cold and it will give to the hot body. So this is the heat engine and the work engine. These are the two concepts of the work engine and heat engine. Coming to the efficiency of the heat and work engine. So for calculating the efficiency, we need work output to the heat supply, means how much work we are getting by supplying how much heat. In that way, we can calculate the efficiency. So here it can be also written as 1 minus temperature of the sink minus temperature of the source. So when we are getting the temperature of the sink and temperature of the source, we can calculate the efficiency of the heat engine. So this is the formula we can utilize for calculate the efficiency of the heat engine. So from this equation, we can see that when we have to increase the efficiency of the heat engine, for that either we can increase the temperature of the sink, means when we are increasing the temperature of the sinks, then efficiency will increase. And on the other hand, when we are decreasing the temperature of the source, then also this efficiency will increase. So this is the concept to how we can calculate the efficiency of the heat engine. Now coming to the third law of the thermodynamics. According to the third law of the thermodynamics, internal equilibrium undergo an isothermal process. The entropy change goes to the zero at temperature goes 0 to the 0 degree Kelvin. That means delta S limit T, when temperature goes to 0, this change of entropy goes to 0. This is the third law of the thermodynamics. This law is valid only for the pure substance of the mixture. And third law of thermodynamics also conclude that there does not exist any finite sequence of the cylindrical process which can cool a body to the 0 Kelvin temperature. Means for any body temperature, when we are trying to attain at 0 Kelvin, it is very difficult to get. This is the third law of the thermodynamics. So here we are discussed with the zero law, first law, second law, and third law of thermodynamics with appropriate examples. Now coming to the next topics, we have discussed some thermodynamic cycles that is actually utilizing for our vehicles and some other applications. So first I am going to discuss the Otto cycle. In Otto cycle, there are 4 processes. In the first process, this is the compression. That means when this piston, this is the piston and this is the cylinder. And I taken the air as a source. So when this piston will go up, the air will be getting compressed. So this is the compression process. So this is the compression process with isentropic. So this is the isentropic compression, we can say. Coming to the next step. In this step, when this piston get compressed, we are supplying some heat. This supplying the heat that you can see here, Q in. Q in means we are getting some heat to this cylinder. That in actual practice happening by some sparking. So this addition of heat occur at the constant volume process. That will explain in the next slide. And when this heat addition at the constant volume occur, so when heat is added, it will be burned, and when it will be burned, it will be increase the pressure. When pressure will be increased, that piston will go downward like this. This piston is coming in the downward direction. So this process can say expansion process, because expansion is happening here. In the last stage, whatever burnout gases that will come out, exhaust gases will go out. So this is the heat rejection at constant process. That means we can see here heat addition and heat rejection both happening at constant volume process, and compression and expansion happening at isentropic. That we can see here in the next slide. You can see this is the 1-2 process. That means we are going from 1 to 2. You can see in the previous slide, means this process. 1 to 2. Compression is happening here. Same thing I represented in the PV diagram. PV diagram 1 to 2 represent the compression. You can see here, this is the volume, higher volume. We are getting to the lower volume. We are moving from higher volume to the lower volume, means point B to A. That means compression is happening, and this compression is happening with the isentropic process. So this is process 1 to 3, we can say isentropic compression. In similar manner, 2 to 3. 2 to 3 explaining this process, 2 to 3 means heat addition at constant volume process. So here we can see 2 to 3, constant volume line you can see, this is the volume curve. So here from 2 to 3, we are not going to change the volume. So we can say here, this is the 2-3 process, and this is the heat rejection, heat addition at constant volume. In similar manner, 3-4 process is the isentropic expansion. In this process, expansion is happening because volume is increasing. From 0.3 to 0.4, volume is getting increased. So this is expansion process. Coming to the last process, 4 to 1, this is the heat rejection at constant volume. So this is the PV diagram. Same thing we are converting to TS diagram, means temperature entropy diagram. In temperature entropy diagram, this same diagram can be represented like this. And then we are going to calculate the efficiency. This is the formula. So 1 minus T1 minus T2. So T1 is the temperature here. You can see here how much temperature we can get, 0.1. This is the T1. How much temperature we are getting at 0.2. This is the T2. So if we are know temperature at 0.1 and temperature at 0.2, we can simply calculate the efficiency of this Otto cycle. And this temperature can also represented in form of compression ratio R. Compression ratio R is nothing but the ratio of V1 upon V2. So when we are having the compression ratio, we can calculate efficiency by using this formula. So this is the mathematical expression by which we can calculate the thermal efficiency of the Otto cycle. Now coming to the next diesel cycle. And apart from this, I also want to tell the applications. Otto cycles are applicable in the all petrol engines. Whatever petrol engines we are using in our two-wheelers or cars, also are working on the Otto cycle. In the diesel cycle, we are again having the 4 process. This is the compression process, constant pressure, heat addition, expansion, constant volume, heat rejection. Only difference is that in this process, heat addition occur at the constant process. But in the earlier case, that in the Otto cycle, heat addition occur at the constant volume. But here heat rejection is again at constant volume. Only difference is that heat addition is occur at constant pressure. And compression expansion are the same. Same thing I represented in the PV diagram like this, you can see here. From 1 to 2, compression is happening at the isentropic. So 1 to 2, we can say isentropic compression. 2 to 3 is the constant pressure heat addition. But in earlier case, that means Otto cycle, it was constant volume. Now it becomes constant pressure. You can see here, this is the pressure line. So pressure are not going to change. From 0.2 to 3, pressure is constant. And coming to the 3 to 4 process, so again this is the expansion. So this is the isentropic expansion, and 4 to 1, this is the constant volume heat rejection. So this is the PV diagram representation of the diesel cycle. Same thing I represented in temperature versus entropy. So this is the TS diagram, same curve. So this is the PV and TS diagram of the diesel cycle. And again, when we are trying to calculate the efficiency of the diesel cycle, we can use this formula. This is the formula for calculating the efficiency of the diesel cycle. Now you recall the efficiency of the Otto cycle. In Otto cycle, only this square bracket term was not there. Otto cycle efficiency was this. So in Otto cycle efficiency, we added this expression, only square bracket expression. We can also see from this expression that a square bracket terms for same compression ratio, it will always larger than 1. So when it will larger than 1, the diesel cycle has lower thermal efficiency because finally it is going to subtract from 1. So anything subtract from 1, so it is going to reduce its efficiency. So we can say that for same compression ratio R, diesel cycle has lower thermal efficiency compared to Otto cycle. For the same reason, CI means compression ignition engine. Compression ignition engine means diesel engine. And SI here, SI means a spark ignition engine. A spark ignition engine means petrol engine. So by this expression, we can say here, compression ignition needs higher compression ratio compared to a spark ignition engine. Now coming to the next thermodynamic process, it is the dual cycle process. In dual cycle process, heat addition occurs at the two types of process. First one is the constant volume process, a second one is the constant pressure process. But in earlier case, like Otto cycle and a diesel cycle, heat addition happening at only one process. Either it is constant volume or constant pressure. So here we are having the 5 process instead of 4. Earlier case we are dealing with only 4, but in dual cycle we have the 5 process. So same thing can be represented in the PV diagram like this. So this is the PV diagram representation of the dual cycle. 1 to 2 is the isentropic compression, 2 to 3 is the heat addition at constant volume, 3 to 4 is the heat addition at constant pressure. So you can see here from point 2 to 3 and 3 to 4 representing the heat addition process. And again 4 to 5 is the expansion and 5 to 1 is the heat rejection process at constant volume. So these are the all 5 process in the PV diagram for the dual cycle. Same all 5 process can be represented in the temperature versus entropy also. So this 1-2 diagram, because this is the isentropic process, so isentropic process entropy is constant. So 1-2 diagram you can see here. This is the no change in the entropy. 1 is the initial position, 2 is the final position. So from 1 to 2 entropy is constant. Likewise, we draw all the process 2, 3, 3, 4, 4, 5 and 5, 1. So all the process in the PV and TS diagram is represented here for the dual cycle. And when we are going to calculate the efficiency of the dual cycle, we can calculate by using this formula. This is the formula for calculating the thermal efficiency of the dual cycle. Sorry. In this formula, actually, you can see here, RC is the volume ratio, that is V3 upon V4, and alpha is the ratio of P3 upon P2. So this is the formula for the dual cycle. So when we are remember this formula for the dual cycle, from this single equation we can calculate the efficiency of the Otto cycle, efficiency of the diesel cycle. Because in this equation, we will put RC is equal to 1. Here RC, when we are going to put RC is equal to 1, so this will become 0, 1 minus 1, 0, and RC is equal to 1, 1 ke power k, this also becomes 1. So in here upper case alpha minus 1 and denominator also alpha minus 1. So this will be cancel out, this all term will go. So only this expression will remain. So this is nothing but the efficiency of the Otto cycle. So you can say here from same expression how we are calculating the efficiency of the Otto cycle. And in same expression, we calculate the efficiency of the diesel cycle also. For calculating the diesel cycle efficiency, we will put alpha is equal to 1. Here alpha is equal to 1, it will become 0. Here 1, then it will become the efficiency of the diesel cycle. So from the single expression, we can calculate the efficiency of the Otto cycle, efficiency of the diesel cycle. And when we are dealing for the efficiency, so there are the two conditions. When the inlet pressure and inlet volume, that means P1 and V1 are the same for the same compression ratio, then that means inlet condition P1 and V1, that means at inlet point pressure and volume are the same and compression ratio are also same. Then efficiency of the Otto cycle will be higher than dual cycle, and dual cycle efficiency will be higher than diesel cycle. So this is the condition when inlet condition, that is P1, V1, and the compression ratio are the same. And again, when we are dealing with the same inlet condition P1, V1, and compression ratio will not same, but peak pressure will be same. Peak pressure means P3, means what is the highest pressure, that will be same, not compression ratio. In earlier case, compression ratio is same. So this is the condition, Otto cycle efficiency will be maximum. But when we are making the condition that the maximum pressure will be same with the initial condition, in this case, diesel cycle efficiency will be maximum and dual cycle efficiency will be little bit less than diesel cycle, and Otto cycle efficiency will be less. So this is the condition. These two conditions you can see here. In this diagram, this is the P1 V1 condition, means initial condition is same. And compression ratio is what? Compression is nothing but ratio of P2 upon P1. So at this point, this is the P2 point here. This two point is the P2, this is the P1. So whatever pressure here and whatever pressure here, we can divide it P2 by P1, it will give the compression ratio. So you can say here, for Otto cycle, this is the condition 1, 2, and 3C 4 1. This is the complete one cyclic process. 1, 2, 3C 4 1. So this is nothing but the Otto cycle. In same process, we can write like this: 1, 2, X, 3B, and 4 1. So this is again the other process. This is the dual cycle, because in this case 5 processes are there: 1 to 2, 2 to X. This is the constant volume, and again X to 3B. X to 3B is the constant pressure. So as I discussed earlier, dual cycle having heat addition at the 2 process, constant pressure and the constant volume. So that is happening here. You can see 3 to X, X to 3B. So in these 2 processes, heat input is happening at constant pressure, volume and constant pressure. And again 3B to 4, this is the isentropic expansion, and 4 to 1, this is the heat rejection process at constant volume. So this is the dual cycle. And the diesel cycle, this is the curve 1, 2, 3A, and 4, 1. So this is the maximum curve. You can see this is the representing the diesel cycle. So you can say here, in this case, diesel cycle efficiency, Otto cycle efficiency, this is the same compression ratio condition. So in the previous slide, for same compression ratio, Otto cycle efficiency is the maximum. So here, Otto cycle efficiency will give the maximum value, then dual, then diesel. And this is the second condition. Then peak pressure is the same. You can see here, this is the P max, peak pressure. P3 is the maximum pressure. That is same for all the process. Here also you can see there are 3 processes combined in the single process. You can see here, this is the 1, 2A, 3, 4. This is what? This is the Otto cycle. Because 2 constant volume line are 2 isentropic lines. So this is the Otto cycle. And again you can see 1, 2B, X, 3, 4, 1. So this is the dual cycle, because here constant volume, constant pressure, there are 2 processes in that heat input are taking place. And again we are taking the extreme curve, that is 1, 2C, 3, and 4, and 1. This cycle is nothing but the diesel cycle, because here heat addition at the constant pressure. So you can see here in all the processes, heat same peak pressure, means P3 is the common for all the process. So in this case, the efficiency of the diesel cycle is maximum. Diesel cycle is maximum, then dual cycle, then Otto cycle. So this is the 2 conditions for the efficiency. Now I'm going to discuss some questions that is already come in some competitive exams. Coming to the first question. First question is that in which path between initial condition A, I, that this one is the initial condition, and final state F, work done is the maximum, the work done is the greatest, means there are 5 processes, 4 processes, A, B, C, and D. So question is asking that in which process give the maximum work done. So I already told in the earlier slide that for calculating the work done, because work done is the path function, it depends upon the path, it is not a point function like internal energy. Internal energy is a point function. So here he asking the work done. So in that case we have to see which curve will give the maximum work done, means maximum area. So D is the curve that will give the maximum work done, because when we are going to calculate the curve area D, area enclosed by curve D, it will give the maximum value. So here maximum work done by calculated by curve D, then curve C, then curve B, and then curve A. Curve A will give the maximum work done. So here question is asking which will give the greatest. So greatest option D will be correct. Option D is the correct answer. This one is the correct A. In same question, if it will ask the lowest, so lowest A will be the lowest button. So if we are arranged in the order, So D will give the maximum work done, then C, then B, then A, according to the area enclosed by the curve. Coming to the next question, here, which of the following process must violate the first law of the thermodynamics? I already discussed the first law of the thermodynamics. The first law of the thermodynamics is the change in internal energy equal to work done plus heat supply. That is the equation of the first law of thermodynamics. So here question asking, which of the following process must violate the first law of the thermodynamics? First option is given, work done if work done greater than 0 and heat is less than 0, then change in internal energy equal to 0. That is possible because change in internal energy equal to work done plus heat. So if same amount of work done and same amount of heat in positive and negative sign, so when we are going to add, it will become 0. So it is possible. So this is not violating the first law of thermodynamics. Coming to the second choice, B. Here work done is greater than 0 and heat is less than 0. In this case, condition is given, change in internal energy is greater than 0. That is also possible because change in internal energy equal to work done plus heat. So if work done value magnitude is higher than heat supply, so in that case, change in internal energy will be greater than 0. So that is also possible. So this second choice is also not violating the first law of thermodynamics. Coming to the third choice, it is given work done greater than 0 and heat supply is less than 0. Means work done is positive and this is negative. In this case, change in internal energy less than 0. That is also possible because in this case, if heat supply is higher and work done is maximum, so change in internal energy will be like W plus Q. So because this is the maximum and this is having the minus value, so this will give change in internal energy less than 0. This is also possible. In the fourth option, it is given work done less than 0 and Q greater than 0. So is it possible that change in internal energy is less than 0? Yeah, is it possible? Because work done is less than 0. That means it having negative sign. Q is greater than 0. That means it having the positive sign. So again, coming to the equation, change in internal energy equal to work done plus heat. So when we are adding these two, so if work done is maximum higher compared to Q, so it will give the maximum negative value. So in this case also change in internal energy can be less than 0. Now coming to the last choice, work done greater than 0, heat supply greater than 0. Means both are positive. Work done also greater than 0, heat supply also greater than 0. But here condition is given, change in internal energy less than 0. How it is? It is not possible because change in internal energy equal to work done plus heat supply. So when we are writing the equation, change in internal energy to work done plus heat supply, these two are greater than 0, then how it is possible it is less than 0? So this condition E violating the first law of the thermodynamics. This is not possible. So this is the correct option. You can take C here. Coming to the next slide. Coming to the next slide, here question is given, a block of aluminium originally having the 80 degrees centigrade temperature placed into an insulated container of water originally at 25 degrees centigrade temperature. After a while of system reaches an equilibrium temperature of 31 degrees centigrade, during the process, therefore option is given. So question is telling that we have one aluminium block, that aluminium block temperature is 80 degrees centigrade temperature. And same aluminium block is placed in insulated container. Container is insulated. That means it will not transfer from the container. But in that insulated container, water is there. That water having temperature 25 degrees Celsius. That means we have one container having water with temperature 25 degrees centigrade. In that water, we are putting one aluminium block that having temperature 80 degrees centigrade. After some times, heat will transfer from the aluminium block to the water because aluminium have higher temperature, 80 degrees centigrade, and water have less temperature, 25. So heat will transfer from higher temperature to lower temperature. So after some interval of time, the final temperature at equilibrium becomes 31 degrees centigrade. This is the question. So he asking delta S of aluminium greater than 0. Delta S S is the entropy. So delta S means change of entropy. Change of entropy for aluminum is greater than 0. First option. Second is given change of entropy for aluminum is equal to 0. Change of entropy for aluminum is less than 0. Change of entropy for aluminum is constant. So here we can see that temperature of aluminum block getting reduced from 80 degrees centigrade to 31 degrees centigrade, because aluminum at initial having 80 degrees centigrade temperature and finally it having the 31 degrees centigrade temperature only. So temperature for aluminum block getting reduced. So as temperature is getting reduced, entropy will also be reduced. So aluminum entropy is reduced means it will going in the negative sign. So change of entropy of aluminum is less than 0. This is the correct option. C. So this option is correct. C. One minute. Okay. Coming to the next question. For which of the following process is the entropy change is the 0? He is given the 4 process: isobaric, isothermal, adiabatic, and constant volume. I discuss all the process. He asking in which of the process entropy change is the 0. In isobaric process, pressure is constant. In isothermal process, temperature is constant. In adiabatic process, heat is constant. So, and constant volume process, volume is constant. So adiabatic process, heat is constant. So change in entropy is 0 possible only in the adiabatic process where heat is constant. So option C is the correct. Coming to the next question, which of the following is the consequence of the second law of thermodynamics? First option is given: heat can flow only from higher temperature to the low temperature. This is possible only in natural way, but we can also do in the reverse. We can transfer heat from low temperature to the high temperature by doing some external bursts. This is possible by the second law of thermodynamics. Second option is given: object in the contact will tend towards the having the same temperature. Third option is giving: any system that produce order from disorder must have external influences. This is the correct choice according to the second law of thermodynamics, because see here, it is clearly written: any system that produce order from disorder. Disorder means, you can say this is the disorder when we are transferring heat from lower temperature to the higher temperature. Means disorder to the order. We are going from disorder to the order. For that, always we have to do some external work. That means external influences we have to provide. So that means C option is correct. For the second law of thermodynamics, any system that produces order from disorder must have the external influences. So this is C option is the correct. Okay, thank you.